Hello everyone. Welcome to the first lecture in a series of lectures on field and Galois theory. Today Aadrita will be delivering a lecture on field extensions. Aadrita, please start.
Yeah. Hello everyone. So we'll be giving a few talks on Galois theory. So I'll be assuming initial course in group theory and field theory. So what is Galois theory? Galois theory is basically studied so that we can translate some problems about polynomials to some problems about groups. Now, there are something called the Galois groups, which help us say certain things about polynomials over certain fields. Now, for example, there's a question, can a polynomial be solved by radicals? Now, we know very well that for degree 2, it's solvable. We know the Sridharacharya formula for which we can get the roots of a degree 2 polynomial. And then in general, what is the answer? So people have found out the solutions for degree 3 and 4, and there has been quite a rush looking for radical solutions for polynomials of degree greater than 4. But it turns out that the answer is no in general. So you cannot find a formula to get the roots of a polynomial which has degree greater than equal to 5. Now this is actually a very easy problem to state, but it turns out that it's quite difficult to solve. So this was solved using Galois theory. This is known as the Abell-Raffini theorem. And this translates to groups as the Galois group. And the problem becomes whether we can write a subgroup of Sn as a solvable group. So this problem translates to whether we can write the Galois group as a subgroup of Sn which is solvable. Now, what is a solvable group? A solvable group is a group that can be written. So G is a solvable group if G, G0, G1, and so on up to Gn, which is the only trivial group identity. So we can decompose G into a sequence of groups such that Gi plus 1 is normal in Gi and Gi mod Gi plus 1 is abelian. So this is what is a solvable group, and this problem translates to groups in this manner. And it turns out that this can be said for Sn, that is n greater than 5, greater than equal to 5. We cannot solve the group, and hence we do not have a radical solution for a polynomial of degree greater than equal to n. So this was our first problem that we will be able to answer. And secondly, for example, we say trisecting. So we can say trisecting an angle. So for example, we know that using a ruler and compass, we can bisect a given angle. Now, what about trisecting it? It turns out, say for the angle 60 degree, and we want to trisect the angle into 3 parts of 20 degrees each. Now we cannot do that. So to show this, we write a polynomial with roots 60° by 3 and other roots. And this can be corresponded with the Galois group Z mod 3Z. So we cannot do this because the Galois group is Z mod 3Z. This can be done only when the Galois group has an order which is a power of 2. But as we can see, 3 is not a power of 2, so we cannot do this. Next in this, something that Gauss did. So Gauss had a lot of dabbling in Galois theory, and well, Gauss is almost everywhere in mathematics. So even here, he proved the construction of a 17-gon, that is a heptadecagon, and this was translated to the Galois group, that is the group of automorphisms of Z mod 17Z, which turns out to be Z mod 17Z star, which is Z mod 16Z. Now,
Excuse me, maybe in the polynomial question you mean with coefficients in rational numbers, or?
yeah, with coefficients and rational.
I see.
Okay, so this I ran out of space. So in the 17-gon, it turns out that we need to look at the group Z mod 16Z, and 16 is a power of 2, and hence we can actually construct a 17-gon using just a ruler and compass. So next, this Galois theory was developed by two people called Abell and Galois, and it's surprising that they both were quite young when they did this. So, okay, now let's look at the main idea. What is the main idea behind this? So we take a polynomial, say an x to the power n, an is a0, which is, let us say, over rational. It's a rational polynomial, and we look at the field f, which is generated by the roots. So if this polynomial is fx, it's generated by the roots of fx. Now we look at the roots and we look at the Galois group. So in this manner, you can say the Galois group to be all permutations of the roots alpha 1 up to alpha n, preserving. So this is the important, it's not just the group of symmetries, it's preserving all algebraic relations. So what are the relations? For example, addition, multiplication, and let us say if we look at the roots of x cubed minus 1, then it will preserve x cubed plus 1, say then it will preserve that the sum of the roots is 0. Okay. Next, this is the old formulation. So this is how it exactly started, because we wanted to find out the roots of the polynomial and work with them. Presently, so the way we will study it will be through field extensions. So our formulation will be something like, we take a field extension, let's say K mod L. So this means K is a subset of L and K and L are fields, such that K is a subfield of L. So we look at the field extension K mod L, and we see the Galois group to be something of the symmetries of L that keep K fixed. So the Galois group is the group of symmetries of the upper group L that keeps the the upper field L that keeps the subfield K fixed. Now let us look at some examples. So say we have the group C. C is the complex numbers and C contains R, and this is the group which has the extension 2. So C can be written as a two-dimensional vector field, vector space over R. Now, what will be the Galois group of this? So it's very straightforward. It's just identity and Z goes to Z bar. So the complex conjugation and the identity element, and this is isomorphic to Z mod 2Z. So this is a example, and in general, so what our main theorem will be, so we'll prove this. This is also called the fundamental theorem of Galois theory, and this is, so suppose we have a field extension L mod K such that it is a Galois extension. Then the subfields of M such that, the subfields M such that M lies between K and L. They have a 1-1 correspondence with the subgroups of the Galois. So we can see that in this example, C mod R, we cannot have any subgroup. We cannot have any subfield that lies between C and R because there are no non-trivial subgroups of Z mod 2Z. And okay, so what does a Galois extension mean? It is an extension which is separable and normal. So these are some terms we will look into and we'll define them later on. And so our main aim is to prove the fundamental theorem of Galois theory and see how this helps us to solve the problems that I mentioned in the beginning of the lecture. Okay, so now let's start with this. First, we'll look at field extensions. Now, like I said in the beginning, if K is a subset of L, it's a field extension if K is a subfield of L. So both L and K are fields, and we write it as L mod K, where L is the higher field. Now we give a few definitions. So first, we tell the degree of the field extension L mod K, and this is denoted by L semicolon K. What is this? This is the dimension of L as is written as a vector field over K. So this can be finite, this can be infinity. And in general, like we saw before, so for C and R, the degree of C mod R, C over R is 2. And the degree of, C over Q, the rational numbers, that is infinity. You cannot write all complex numbers as a finite dimensional vector field over the rational numbers. Okay, and let us look into polynomials and what we will define to be algebraic and transcendental numbers. Okay, so we take a field K, and we take the number, say alpha in K. So let us take L mod K and we take alpha in L. Now you define a map phi from Kx. So this is the field of, this is the ring of polynomials with coefficients in K, and we map it to K alpha. Now this is easy to check that it is an onto ring homomorphism where a polynomial G goes to G alpha. This is surjective. All right, now we can have two cases. So the first case will be the kernel of phi. This can be trivial, and the second is the kernel of phi is not trivial. Now if the kernel of phi is trivial, then sorry, not trivial. If the kernel of phi is, we don't write just the set, we write the ideals generated by 0. So here we say that if the kernel of phi is this, then the number alpha or the element alpha that we took from L, this is transcendental. And suppose we can write, and suppose the second, if the kernel of phi is not 0 ideal, then we say that alpha is algebraic. Now this was a very abstract definition. Let us look exactly what this means. Okay. So what is an algebraic number? In general, in the common field theoretic language, what we can say that alpha is algebraic over K if alpha is a root of a polynomial of, let's say, f x, which is in K. So we had alpha in the upper field L, and we took the, what was our definition? So we had the function phi, which went from Kx to K alpha. And we said that if the kernel is non-trivial, then we call it algebraic. So how does it translate to this? So if the kernel is non-trivial, what does that mean? So that means there exists a polynomial f such that f of alpha is 0. So that is exactly what we are saying here. So if we have a polynomial in the ring of polynomials over the field K, then alpha is called algebraic. And what is transcendental? So anything that is not algebraic is transcendental. So if alpha is not algebraic, it is transcendental. Okay, so these are some definitions. Now let us look at something transcendental. Now, in the lectures, in the seminars that we had organized, we had the first talk on which proved that phi is irrational. So phi is transcendental. And transcendental over Q, because of course phi is not transcendental over R. We can write phi as phi itself. And in general, this is very difficult to prove. So numbers like pi and d, these are transcendental. But let's say root 2, this is not transcendental because we can write x squared minus 2. So root 2 is a root of this polynomial, which is in Qx. So root 2 is not transcendental over Q. And in general, we can look at the field. So, okay, recall that if we have an irreducible polynomial in kx, sorry, so if f is irreducible, then kx quotiented by the ideal generated by f is a field. And note that this field contains the field k. So we can write, if I call this field as L, then L is a field extension of k. And here we can see that the polynomial x, that the element x in L is transcendent over k. Because we just cannot take a polynomial in k and write x as the root of that polynomial. All right. Then finally, we define the minimal polynomial. So our next definition is the minimal polynomial. We take the element alpha in L. So if alpha is algebraic, then we have the polynomial f in kx such that first f alpha is 0, and second, if g alpha is 0 for any other g, then f divides g. So then we call f to be the minimal polynomial of the element alpha. Okay, next we will look at the final definition that.
So you mean alpha is algebraic and f is non-constant, right? I mean
yes,
non-zero.
F is non-zero. Yes, f has to be non-zero. Okay, and yeah, so the final thing will be the degree of alpha. So what is the degree of alpha? Degree of alpha is the degree of the minimal polynomial. Okay, so first we'll give our first theorem, that is first theorem. So we say that so this is an equivalence. So alpha in M is algebraic over K if and only if alpha is in some finite extension of K. Okay, now this is a correspondence between the polynomials and the sub. So we take alpha in a field extension of K, we call that M, and that is algebraic, implies there is some field extension in which contains alpha and which is a finite extension of K, and vice versa. So note that M need not be algebraic. M need not be a finite extension. M can be a infinite extension and we can take it in N, but it can be if it belongs to a finite extension, then it's algebraic over K. So for example, in our previous example of Q, root 2 belongs to the set of complex numbers C, but root 2 is algebraic because it belongs to the field Q root 2. So this. So it belongs to Q root 2 and C. So if I take, say, pi in C, it is transcendental, but if I take root 2, it belongs to Q root 2 and that is a finite extension. So there we can say that root 2 is algebraic. Okay, now let us look at the proof of this theorem. So first we show that finite extension implies algebraic. So what do we mean? So suppose we have L mod K, then L is a finite extension of K. That means I have a basis of alpha 1 up to alpha n, such that L is a vector space over K, where alpha 1 to alpha n belongs to L. And what we do is we take the numbers, say 1, alpha, alpha square up to alpha to the power n. Now you see we have n different elements and they are all distinct, because if they are not distinct, then we can write them as an equality, and then we get alpha to the power k equal to 1, which makes it algebraic. So we are assuming that alpha is algebraic. So we get the finite extension. So we get that alpha is algebraic. So assume that, I should have written this down. So assume alpha is algebraic. And so alpha is not algebraic. Wait. All right. So assume hello. I'm sorry, my internet had some issues. So, all right. So we have a set, say S, which is of cardinality n plus 1, and this has to be linearly dependent. So we have some constants. So say a naught plus a1 alpha plus an alpha to the power n, which is equal to 0. And we can write this as the polynomial. So fx equal to a naught plus a1x plus anx to the power n. And alpha is the root of this polynomial. So we have one polynomial such that f alpha is 0, and this is a finite degree polynomial, and hence alpha is algebraic. Okay, now we look at algebraic implies there exists a finite extension. So how do we go about this? So for this, we will use the fact that if we have an irreducible polynomial, then the ring of polynomials quotiented by that is a field. So we have the element alpha. We know alpha is algebraic, and we take the minimal polynomial of alpha, and we call that f. So then we look at kx quotiented by f. Now this is a field, and this contains alpha. So alpha is the root of this. Alpha belongs to this field extension, and note that this is an extension of K. Right. And secondly, note that the degree, so we have, let's call this L. We will have some notational ease. So if we have the polynomial, if we have the extension, L is equal to Kx mod f, This is an extension of K, and the degree of L over K is N, which is the degree of the minimal polynomial. So we can say that the image of this thing. So if we say that this is actually the polynomial, a field which consists of polynomials, then we can map kx mod f. We can map it to the field say M, so which contains alpha. Then we can say that x goes to alpha. This is an embedding of L in M, and the image of this field, so if I call this phi, then the image of phi, this is a field containing alpha, and this is a finite extension because we just saw that the degree is n, and hence we see that if alpha is algebraic, then it belongs to some finite extension of the underlying field K. All right. Let's look at the next theorem. So here we have a tower of extensions. So we have at the bottom K, then we have L, then we have M, and we have the degree of M over K. So what is the relation between the degree of M over K and the degree of the fields lying in between these? So the degree of M over K is actually equal to the degree of M over L times the degree of K over L. Now this is quite easy to prove. So what we do is we take the basis of, so we have the basis B1, which is the basis of M over L. Then we take the basis B2, which is the basis of L over K. And then we say that this is x1 up to xn, and this is y1 up to ym. Then we consider the basis xi yj, such that I is from 1 to n and j is from 1 to m. Then this basis is the basis of m over L. Oh, okay, I made a mistake. So this will be L and this will be K, because L is the large, of course. So we get the tower of field extensions, and we get that the degree is actually multiplication. Okay, and now nice corollary. So suppose we have two elements, say alpha and beta. These are two field elements in L over K, and suppose they are both algebraic. Now the corollary would be alpha plus beta, alpha minus beta, alpha times beta, and alpha by beta. They're all algebraic. So this might seem like a very obvious fact, but it's actually quite difficult to prove. So if you have something like, say, root 2 plus 15th root of 3 plus the 9th root of 17, then to prove that this is algebraic, you will have to do a lot of calculation, and this is very computationally intensive to find the polynomial and show that this is algebraic. But we have a very nifty little way. So what we do is we take K, then we attach alpha to K, and then we attach beta to K alpha. So K alpha. So we know that alpha is algebraic over K and beta is algebraic over K. So this is a finite extension and this is a finite extension. So on the whole, this is a finite extension, and this is a field which contains alpha, beta, alpha plus beta, alpha minus beta, and hence all of these elements, which can be written as a combination of alpha and beta, are algebraic. Okay, So there's a quick corollary to this. So this was our first corollary, and the second corollary would be, so either e plus pi or pi times e are transcendent. It's a very long open problem. So we know that e and pi, they are individually transcendental, but what about their combinations? What about e times pi, e plus pi, to the power pi, and other combinations? Well, we don't know whether they are transcendental or algebraic, but what we can say that one of them is transcendental. So either e plus pi is transcendental or e times pi is transcendental. So how can we say that? We can say this because suppose we have the polynomial x square plus, sorry, this would be a minus, pi plus e x plus pi times e. So we have this polynomial, and what we can see that pi and e, these are the roots of the polynomial, and we know that they are transcendental. So this is pi and e, this is the root of this polynomial, and if both of them were algebraic, that would imply the individual roots are algebraic, because this is a polynomial in the field containing pi and e. All right, and this is our recap of field extensions. So next we move on to splitting fields. Now, what are splitting fields? This is a so we take a polynomial, and we right now we saw that we are interested in what are the roots of the polynomial. So say we have the polynomial p, which is in kx, and we want to find an extension of an extension L of k, such that all the roots of p belong to the field L. Now, what do we mean by this? So we can have multiple fields, but what we want is the smallest one among them. So the first condition that we want is p splits, sorry, no, we don't write splits, so p factors into linear factors. So we have the field L, where we can factorize p into c, p minus alpha 1, x minus alpha 1, x minus alpha 2, and so on. And secondly, we can, the second condition is that L is written as k times alpha 1 up to alpha n, where alpha 1 up to alpha n are the roots of the polynomial p in that field. Okay. Then we call L is called the splitting field. Okay. Now we given a polynomial, we want to look at its splitting. So before we continue, let's look at some examples. Okay. So first, now we have the linear polynomials themselves. Now this, if we say this is a polynomial in kx, then kx itself is the splitting field of this polynomial. Okay. Next we have the quadratics. So x squared plus k1x plus k2. This is in kx. Now if this is reducible, that is, we can write it as, we can factorize this, then of course we can write it as linear factors, and then kx itself is the splitting field of the polynomial. So if I call this f, so kx is the splitting field of f. And suppose that this is irreducible. Then we have the root. So we can write kx quotiented by f. This contains the root alpha because it's a polynomial and it has a root, and we we add the root to we can have the root somewhere, so we quotient it, and we know that this has the root by the previous. In the proof of the previous theorem, we saw that alpha is a root in this field. So if we call this L, then so we have two roots, alpha and beta, then alpha is in L. Similarly, beta is in L because alpha plus beta is A1 and A1 is in K. Right. So if alpha can be written, if alpha belongs to L, we know A1 belongs to L. So then beta, which is equal to A1 minus alpha, this belongs to L. Okay. And this was the degree 2. So what about degree 3 polynomials? Say we have the polynomial x cube minus 2. And we say the underlying field, this is over Q. So we have the polynomial x cube minus 2 over the field Q. Then we know we can factorize this over R as x minus cube root of 2 times x squared plus cube root of 2 times x plus cube root of 2 whole square. This is a factorization of our polynomial. And let us say we adjoin this root. So we have q, and we can write q cube root 2. So we have one root here, but we can see that we do not have the other two roots because, well, the other two roots are, say, alpha and beta. These are both complex roots because we can see that this polynomial is this will be square root 2 times omega and cube root 2 times omega and cube root 2 times omega square. This polynomial has discriminant negative, hence the roots are complex and they cannot belong to the field that is generated by q and the cube root of 2. So what we have to do next is we need to add another root to this. So we have q. So this has cube root of 2 comma cube root of 2 times omega. Okay. Now, this was q quotiented by, okay, I didn't give it a name. So this is fx. So q quotiented by f, and we call this to be L. Then this is equal to m, which is equal to L quotiented by, we factorize it at p and q. Then this is q quotiented L quotiented by q. So we have the following. We have the field k, which is equal to q. Then we have L. Then we have m. So what? Let us look at the degrees. So what is the degree here? So L over q. So the degree was 3. So we quotiented by f, the full polynomial. So this has degree 3. Next, we quotiented by this quadratic. So this has degree 2. So the whole field, m over k, this has degree 2 into 3, which is equal to 6. Okay. Next, we look at for what we saw previously, that we had a degree 3 polynomial, which gave us a degree 6 extension. Let us look at another example. So this is again a degree 3 polynomial. Okay, so we say that the polynomial is px, which is equal to x8x cube plus 4x square minus 4x minus 1. Yeah, so this is the polynomial, and it turns out that the roots of this polynomial are cos 2 pi by 7, cos 4 pi by 7, and cos 6 pi by 7. Now we have these three roots, and These are not in Q, so these do not belong to Q. This is in Q, and this is not in Q, and this is in QX. Sorry, and this is not in Q. So Q is our K. So we can write K as a subfield of Kx, quotiented by the polynomial P. And so we have the root alpha, and we know that we can write cos 4 pi by alpha, sorry, 4 pi by 7 as 2 times cos 2 pi by 7 square minus 1, the square formula. And we can write cos 6 pi by 7 using the cube formula. So this is the formula of cos 2 theta, and we can write similarly for cos 3 theta. We can write it in terms of cos theta. And so we can say that this is just an algebraic combination of the root alpha, and hence we have these roots in the field K. So this is a degree 3 extension because we quotiented by a degree 3 polynomial. So this has degree 3. So now we saw that a degree 3 polynomial can have a degree 3 extension. All right, and so this was a degree 3 where we have a different degree extension. We can also have degree 4 polynomials with certain extensions and so on. So the next question that we ask ourselves is that, okay, these were some specific polynomials. What about general polynomials? So the theorem says that for any polynomial f in Kx, there exists a splitting field for f. Now, excuse me for a minute, I'm out of pages. Okay, so we would like to see if there exists a splitting field, and we have the theorem that says that indeed, given a polynomial over the field Kx, we have a splitting field. Now, how do we construct the splitting field? So say the polynomial f, this is factored into polynomials p1, p2 up to say pk. So, and each of these polynomials p1 up to pk are irreducible, and hence they are prime. So what we do is we say the field k1 equal to kx quotiented by p1, the ideal generated by p1. And then we have a field k1, and we see whether any other polynomial p2 to pk, they are in this polynomial k1, and then we get the polynomial, say, and k2 is k1x quotiented by p2, and so on. And hence we finally get a field, say k, we get a field L, which has the roots of all the polynomials, p1 up to pk, and hence of f. So given a polynomial f, we can always find a field L such that it is the splitting field of f. So the next question that comes up is that, okay, so this was a specific construction of the splitting field. So we first took P1, then we took P2, and so on. What about a different permutation? So if I start with P2, I quotient by P2, then I quotient by P3, and then P1, and so on. What about that? So then I get a different field extension. Are those two the same? Are they different? And if so, then how different are they? Next theorem that says that they are not much different. So if we have two splitting fields, so we have L, L prime. These are the splitting fields of F. Then L is isomorphic to L prime as extensions of K. So what do you mean as extensions of K? So these are two different splitting fields. So they are different as fields, but they have the underlying embedding of K within them. And this is quite easy. This is not quite easy, but the proof is fairly technical. So what we do is we have the field K and we have the splitting field L, and then we say we take another field K prime. So we have the polynomial F written as P1 up to Pk, small lot of K's, and we translate this to the polynomial, say F prime, which is P1 prime up to Pk prime. So the permutation that we were talking about. And then we take another extension L prime over K prime. So we get two different splitting fields. Then we want to know what is the relation between these two. And as we said that this is isomorphic. So what we do is we take K1 alpha, and that is the root of alpha over here, and then we take K2 alpha and so on. And then we keep adjoining the roots and we get to L. And since we are doing similarly in one side, we get to L prime. And this way we get that degree of L is less than equal to degree of L prime. And since both are splitting fields, we can reverse this. And we get the degree of L prime is greater than degree of L, and hence they have the same degree, and they are the field extension over K and K prime, and these are the same fields with the different permutation of the polynomials. So L and L prime are isomorphic because K and K prime are isomorphic. Okay, but there is a catch here, which I would like to mention. So for example, this isomorphism that we gave here is not unique. There can be a different isomorphism between two different splitting fields, and this can lead to certain glitches when we move ahead. So for example, we have R, and we know that we can see C as an algebraic extension. So we adjoint Ri, and we also have something called Rj. Instead of I, we write J. Then we have an isomorphism. So what can the isomorphism be? So I can go to J. Similarly, we can have another isomorphism where instead of I going to J, the I going to minus J. So there are two different isomorphisms between these groups, and there is this subtlety that often we can just identify them up to isomorphisms, but the isomorphisms are not canonical. They are different. So this can lead to some glitches. And next, what we will look at, so I'll just give a definition because I am out of time today. So the next definition will be of normal extensions. Okay, so the normal extension is what we did. We took a polynomial f in kx, we got a root alpha, and we made the extension of L over K, and we said alpha is in L, and so on. So we kept stacking it up. We kept adding the roots to K, and we kept getting higher and higher field extensions, and all of them finite. And we finally reached a point where we did not have to add any more roots, and we got a splitting field. So what is a normal extension? A normal extension L of K is such that if you have a root alpha in K of if you have a root alpha in L, then you have all the roots. So what it says that instead of stacking from K to K alpha 1 to K alpha 2, alpha 1 up to K alpha 1 up to alpha n, instead of stacking one by one, if you add one of the roots, then all the other roots automatically come into the extension. So these are called normal extensions. So to study normal extensions, we will first have to go through algebraic closures. Now, what is an algebraic closure? What we saw till now was that given a polynomial f, there exists a splitting field. Now, what about all the polynomials? Now, this kx is a ring of all the polynomials over k. So, given one polynomial, we can get a splitting field. Now, what is an algebraic closure? An algebraic closure says that if you take any polynomial k, it has all the roots in the algebraic closure. So, we know that C is the algebraic closure of R. And in general, for general fields, we look into the theory of algebraic closures in our next talk. And thank you. Any questions?
So I don't think there are any questions. Thank you, Aadrita, for the talk. Join us again this Saturday for next lecture, which will cover the discussion on algebraic closure and finite fields. Thank you.